I am Andrew Chen. I am a newly formed program manager here at Google, but for the past 2 years I've been a technical writer on Kubernetes. And this is Dominik Tornow. He's a director of engineering at SAP, and we've been working on this project together for the past 6 months. So we're trying to use modeling to help conceptual understanding. All right, so let's begin. So like I said, I've been a technical writer on Kubernetes for the past 2 years. And honestly, for most of those 2 years, I don't think I understood Kubernetes very well. You know, I could document some features and specific uses, but most of Kubernetes still remained inaccessible to me. And I was wondering, is this just me? Just a quick show of hands. For all of you who have worked on Kubernetes, was it difficult for you when you first started to understand Kubernetes? Anyone? Yes. So why is Kubernetes so hard? And does it have to be this way? So I met Dominik, and he introduced me to formal and conceptual modeling. And it blew my mind, because that's when I realized I didn't really have a solid mental model of Kubernetes, how Kubernetes works. And then even more than that, I realized that it didn't need to be that way. So Dominik showed me that the models were the key to having a coherent and accurate picture of Kubernetes. So now I can confidently talk about Kubernetes because I actually understand how it works. So Kubernetes doesn't have to be hard to understand. It is possible to walk users through the process of building up a clear and accurate mental model so that they can reason about the system. So with that, Dominik is going to talk a little bit about modeling first.
Thank you. Yes, so before we discuss how to reason and how to write about Kubernetes, I want to briefly discuss how to reason and write about software systems in general. A fundamental concept of reasoning is the concept of a mental model. Psychologists argue that we apprehend the world by building inner mental replicas of the concepts and their relationships that concern us. So for this presentation, the term mental model refers to a set of internalized facts about a system. These facts capture the concepts and their relationships that make up a system. So a mental model enables us to reason about a system. Informally speaking, the term mental model refers to everything we know about a system. But how do we acquire a mental model? There are 2 ways to acquire a mental model. The first is via research and development. If you study or if you build a system, chances are pretty high that your mental model is accurate. But research and development is reserved for engineers. Luckily, the second way is via technical communication. Therefore, technical communication refers to the transfer of a mental model from a source to a target. According to this definition, the task of a technical writer is to facilitate that transfer. When the transfer completes, the target shall have the same mental model as the source. Therefore, a technical writer is an intermediary performing 2 steps. The first step is the transfer from a source engineer to the technical writers themselves. This step in the literature is called invention. The second step is the transfer from the technical writers to a target engineer. This step in literature is called delivery. In practice, each step suffers information loss. When the transfer completes, the mental model of the target is at best incomplete and at worst inaccurate. This illustration implies that technical communication is indeed a high-stakes round of the children's game telephone. So the fundamental challenge we face is to increase communication efficiency and therefore minimize information loss. I believe to increase communication efficiency and to minimize information loss, a technical writer should understand the system they write about in every relevant detail. Now, this statement may not line up with your individual experience. You may have created documentation without understanding the system in every detail. You may even believe you cannot understand the system in every detail. After all, you're not an engineer. Well, maybe not everybody here has the capacity to construct a software system like Kubernetes. But everybody here has the capacity to understand a software system like Kubernetes in every detail. People may just not have the tools. So we propose to use conceptual and formal models to maximize communication efficiency, to minimize information loss, and to enable non-engineers to understand the software system. Because with an accurate and concise understanding, with an accurate and concise mental model, you will be able to confidently create accurate and concise documentation. But before we address the practical side of modeling, we shall briefly address the theoretical side of modeling. The fundamental idea is that two people will arrive at the same mental model whether they study the system or a model of the system. But what is a model? A model is an abstraction of a system. It is an abstraction of a system so that every fact about the model is a fact about the system. So informally speaking, what is true for the model is true for the system. In this particular example, the model states that there is an electric circuit composed of a power source and a light bulb. This particular model does not state information about electric potential of the power source or the resistance of the light bulb. Hierarchies to the rescue. Models create hierarchies. Additional models add additional detail. So the second model here adds facts about electric potential of the power source, and the third model adds facts about resistance of the light bulb. Studying the sequence of models, each adding more detail, enables the reader to build a concise, accurate understanding of the system. But what constitutes a suitable language to describe software systems? Well, any software system is a dynamic, discrete system. And any dynamic, discrete system can be modeled as a state machine by specifying the set of possible behaviors. Formally, a behavior is a sequence of states, where a state is an assignment of values to variables. Now that is a mouthful, maybe best illustrated with a simple example. In this example, we will briefly outline the state space and the behavior space of the traffic light control system of a simple intersection. Traffic may flow in vertical or in horizontal direction. In this example, there is a set of two variables, NS representing the traffic lights in vertical direction, and WE representing traffic lights in horizontal direction. Each variable may be assigned one of two values, red or green. Combinatorially, that leads to four states: red, red, green, red, red, green, green, green. No surprises there. For a safe traffic light, there are four different state transitions. From denying all traffic, we may enable traffic flow in the horizontal or vertical direction. However, for rather obvious reasons, we may never enable traffic light or traffic flow in both horizontal and vertical directions simultaneously. States and state transitions may be represented graphically, as depicted in the previous slide, or textually as formal specifications as depicted in the current slide. Here, states and transitions are represented as TLA+, shorthand for temporal logic of actions. A TLA+ specification consists of mathematical formulas. Mathematical formulas slice through ambiguity and uncertainty like a sharp knife through a loaf of bread. We created a set of mathematical formulas that models various components of Kubernetes, like different controllers and the scheduler. We found that with little training, non-engineers are capable to interpret graphical and formal specifications and build accurate mental models and a solid understanding of the system. To conclude our example, over time, when the system transitions through the state space, we are able to observe the familiar pattern of alternating traffic flow. Any software system may be represented in terms of state and state transitions. This fact enables a common, standardized language, a meta model that is able to describe the static aspects, the dynamic aspects, and the value ranges of any software system concisely and accurately. The next part of the presentation focuses on Kubernetes and applies the discussed modeling theory and modeling practice to explain what Kubernetes is, what Kubernetes does, and how Kubernetes does that. With that, I hand over to Andrew.
All right, so now let's apply some of this modeling to Kubernetes, and we're going to start at a high level, right? And then we will add more detail. So in this presentation, we want to explore like how to think about Kubernetes, right? We want to talk about like what it is, you know, what does it do, and how does it do that? So what is Kubernetes? Kubernetes, this is the definition we landed on. Kubernetes is an infrastructure automation engine designed to manage containerized applications, right? So according to this definition, Kubernetes automates the management of applications. You know, Kubernetes manages your infrastructure to be able to manage your containerized application. And this is, I'll talk about, you know, where the automation comes in. But before that, let's talk about kind of old school. So like when I came into the industry out of school, right, this is how it was. There's a sysadmin, you know, there's a server, and the sysadmin would execute binaries to get processes. And this is the world that we lived in before. But then came along containerization. So then binaries were replaced with images, and processes were replaced with containers. So then let's take a simple scenario with you know, a containerized system, right? So there's a user and there's a container runtime. So the user has to manually execute one of the container images, which execute, you know, container C1 using the image busybox, right? And then this results in a running container. And so the user, if they want a second container, then they do the same. They do another command, which would be, you know, run container C1 with busy. Oh, but before that, say they want to see what's going on in the system, they can request, you know, a list of the running containers, and so they can see, oh, there's C1. It's using, you know, the busybox image, and it's running.
So to come back to am I on? Yes. To come back to states and state transitions for a second, take note how Andrew describes the system in terms of a state machine. The user triggers the action create container C1 that transitions the state S1, where the set of containers is empty, to the state S2, where the set of containers consists of one container.
So now the user wants to run a second container. So again, they send a command, and the second container is running. But what if one of these containers terminates unexpectedly, right? Then the user has to manually execute it again. And so they send another command, and the container's running again. So now both containers are up and running.
Andrew continued the explanation of manually managing the infrastructure and walked us through the state transitions from S1 to S5, where C1 was created, C2 was created, C2 was terminated, and C2 was recreated.
So now let's bring in Kubernetes. You know, where does Kubernetes fit into all this, right? So Kubernetes automates this process. It sends commands on behalf of the user, and the user can give configurations to Kubernetes. And then the feedback is collected by Kubernetes and is reported as a status to the user, which is simply the aggregation of all the feedback, right? So in this scenario, the user sends a configuration to Kubernetes which says, I want 2 containers up and running. Kubernetes then executes the command, and one of the containers is running, executes the second command, the second container is running. Then, if one of the containers terminates unexpectedly, Kubernetes acts on the user's behalf and then executes the command again to get a new container, right?
So with the addition of Kubernetes, we added a second variable to the system. This variable contains the user's configuration and enables Kubernetes to trigger the very same sequence of actions as the user did in the previous scenario, creating C1, creating C2, and recreating C2 after termination.
So this previous scenario may not be that interesting, but when you're only dealing with a handful of containers. But when you have a large data center that's composed of like hundreds of machines or thousands of containers, it quickly becomes unmanageable without automation, right? This is where Kubernetes comes in. So in addition to container runtimes, Kubernetes can also manage other parts of the infrastructure, such as load balancers and storage managers. So Kubernetes manages your application and its associated infrastructure on your behalf, which enables you to have scalable and reliable applications, which is what we're all going for. So now, how does Kubernetes actually do this, right? So you can divide the system into two parts, the control plane and the data plane. The control plane is where the management logic is performed, and the data plane is where the execution is actually performed. Right? So if you look at this diagram, you can see that the user passes a configuration to the Kubernetes control plane, then the control plane manages the data plane on the user's behalf. So as you can see then, like there's actually a very well-defined edge to the data plane, right? There are these interfaces, like the container runtime interface, the container network interface, the container storage interface. And these channels are what the Kubernetes control plane uses to communicate with the data plane. Right? And so actually what we think of as Kubernetes is really the control plane. Now let me turn it over to Dominik, who's going to dig a little bit deeper.
So Andrew just explained the high-level behavior. Now I would like to jump into a concrete example. And for that, I have a quick question for the room. Who here heard of pods, and who here knows what a pod is? So anybody wants to share their definition of pods, or should I make Andrew do it? Andrew, what's a pod?
A pod is a set of containers.
Alrighty. So the documentation states that a pod is a set or a group of containers. Personally, I do not like this definition. A pod is an element of the Kubernetes control plane, and containers are elements of the Kubernetes data plane. Instead, we use a definition of a pod represents the user's requests to the Kubernetes control plane to execute one or more containers on the same node of the Kubernetes data plane. Granted, it does not roll as easy off the tongue as a group of containers, yet it depicts a pod accurately. Second question, who has heard of Kubernetes objects and knows, of Kubernetes deployment objects and knows what a deployment object is? Andrew, go give it to me.
A deployment is how you run an application on Kubernetes.
Informally, we say that a Kubernetes deployment object represents an application. But that doesn't even scratch the surface. According to the documentation, a Kubernetes deployment object represents the desire to maintain a stable set of replica pods running at any given time. Kubernetes will move the current state to the desired state. For example, a Kubernetes deployment object represents the desire to maintain a stable set of 2 pods running at any given time. If there is less than 2 pods, Kubernetes will create pods. If there are more than 2 pods, Kubernetes will delete pods. So maybe you can tell by my demeanor, I don't like this definition either. So let's see behind the curtain and build a solid mental model of how Kubernetes deployment objects actually work. This diagram illustrates the high-level component architecture of Kubernetes. Illustrated in the center is the Kubernetes API server, the database, the brain of Kubernetes. All Kubernetes objects, whether deployment objects or pod objects, are stored here. Illustrated on the left are Kubernetes various controllers in the scheduler. Illustrated on the right are individual worker nodes. Each node hosts a Kubernetes kubelet and a container runtime. This diagram already reveals that the individual components of Kubernetes do not communicate directly. They communicate indirectly via the Kubernetes API server. This pattern is known as do not share state by communicating. Communicate by sharing state. This slide is my Achilles heel. Kubernetes controllers are central components of the Kubernetes control plane. The controllers perform actions on the user's behalf. Controllers operate independently of each other, and the controller follows one rule and one rule only that may not make sense right now but will make sense afterwards. If an action is continuously enabled, that action will eventually be taken. Full stop and period. Very abstract. However, let's look at this in practice. Let's follow the steps Kubernetes takes to process a deployment object. Here, the user creates a deployment object with a replica count of 2 pods. The presence of a deployment object enables the deployment controller to create Kubernetes replica set objects. In turn, the presence of a replica set object enables the replica set controller to create Kubernetes pod objects. Since the deployment object states that 2 replicas shall exist, the replica set controller will create 2 pod objects. In turn, the presence of a pod object enables the scheduler to assign a Kubernetes pod object to a worker node for subsequent execution. First for the pod P1, then for the pod P2. In turn, the presence of a pod object that is assigned to a worker node enables the kubelet on the node to execute a set of containers excuse me, to execute a set of containers, in this example 1 container. So the presence of a Kubernetes deployment object enables Kubernetes to create a set of replica pods P1 and P2. In turn, P1 and P2 result in the execution of a set of containers on a set of worker nodes. The end. Let me state it again. If an action is continuously enabled, that action will eventually be taken by every controller individually, without ever coordinating, without ever communicating to each other, only by constantly looking at the Kubernetes object store. Now, please note how I walked you through one particular behavior, but Kubernetes may take many different terms. Whenever an action is enabled, that action may be taken. So for example, pod P1 may be scheduled and executed before P2 is ever created. Kubernetes does not adhere to any particular order of steps. Any action that is continuously enabled will eventually be taken in any order.
Okay, so how do we apply this modeling to Kubernetes in Kubernetes documentation, right? So abstractly, what we're trying to do with this project is create sort of a canonical source of truth, right? We want to take all that knowledge about the system and put it in one place where then everyone can understand it in the same way. And then technical writers can take that and with their understanding then write the documentation and then have a more efficient and accurate way to communicate this to the reader, right? So what Dominik and I want to be is like the peer resource to you guys, the technical writers and other people in the Kubernetes community, so to help you understand it better, so then we can all do our jobs better. So we created, so we have sort of a modeling working group going on. So we created a channel in Slack. So if you'd like to understand Kubernetes better while you're writing your documentation, please feel free to contact us, reach out to us through this Slack channel, and we can work together. So we've been at this for like 6 months, but we are not near completing. We've just kind of scratched the surface and have the tip of the iceberg, but we'd like to create sort of some source material that other people can use. A lot of the work that we've done so far has been writing blog posts on medium.com, which some of you may have read. And so we want to amass a bunch of these models and diagrams and other things like that that can be used to help explain Kubernetes. So please feel free to reach out to us. And then, do you want me to kill the...
Oh, we can first open for questions, right?
Yeah, okay.
Yeah. Are there any questions at that point? Please.
The medium or web addresses for the models that you guys put up so far?
Oh, yeah. We can probably send out a link to them later on, because there's probably no quick link to them on Medium.
Are there some ties to the SIG-Docs group? Is there are these models available in the same documentation website as the other group?
Sorry, say again?
Is SIG-Docs modeling related to the SIG-Docs group? Can you actually?
Yeah, so we've been working, but we haven't actually rolled this stuff back into the Kubernetes.io documentation yet, because part of the process has been writing these blog posts to get feedback and then validating the models. So we're just at the point where we think we can start integrating it back into the documentation set.
Andrew, can you repeat that question?
Oh, sorry. So the question is this project related to the Kubernetes SIGDocs group? SIGDocs is the special interest group for documentation there. And so we have been part of SIGDocs. I was the co-chair for a while, but we're trying to amass, sort of the source material before we start folding it back into the actual official documentation. Any other questions?
What was the process that you used to establish the models?
Good question.
That is a good question. So there is not necessarily a strict process to it. So there was some top-down, there was some bottom-up, there were some interviews, there is some or a lot of reading the code. So you are basically like fishing in the dark, right? And it took us a considerable amount of time to actually come up with this. What you just saw is still a limited set of models about Kubernetes, and yet there is still not necessarily consensus about it, and we still did not arrive at a definition for each and every concept in Kubernetes. So it is pulling teeth in here.
Yeah, a lot of these diagrams that you see, they look simple now, but actually they took a long time to create and simplify. Like the high-level architecture diagram, for example, the first version we had a lot. Yeah, it had a lot of stuff in it, and it was like kind of confusing. And it took a while to kind of iterate and improve on it. And then I witnessed Dominik. He looked through the source code, right? We also interviewed several engineers because we have to like validate these models. So we would ask them questions. Like it almost felt like we were interrogating them because we were asking them kind of edge cases, like, well, what does it actually do in this case? And they would think about it, and then they give us an answer. But then that would help us see like what the system actually does, right? And then I think Dominik also read through blog posts and all sorts of documentation. And then we would also have a lot of discussions, kind of bouncing things off, like, how about thinking about it this way? Does this make sense? Is this accurate? Like, does this help people understand it? So it was a non-linear and fairly lengthy process.
That is a very elegant description, non-linear. But let me state one thing. I do realize this is not directly your question. However, when you try to describe a system, when you document a system, when you model a system, right, follow the system's construction. Try to figure out what it actually does, not what you want it to do, right? It may sound elegant, pithy, right, to say something like declarative system, desired state, right? But is this really truly how the system is built? If you follow the path, how the system is actually built, then you're not communicating your personal take on it, not your philosophy, but you're just communicating fact and the truth. That is usually my guiding principle. And as Andrew said, the process is very nonlinear.
Also, I think one thing to note is the limitations of analogies, right? Because I hear out there a lot of people say, yeah, use analogies as much as possible, because then people can understand. And yes, maybe, but the limit of analogies is that the new user doesn't know where the end of your analogy is, right? So as the expert, you may know what your analogy covers, but then if they try to extend it, they may be inaccurately reasoning about like what you mean. So we try to avoid using analogies, and if we do, we try to be very specific about like what the analogy covers.
Remember in the beginning when we Remember in the beginning when we stated that every fact about the model is a fact about the system, right? For analogies, that is not true. Some facts about the model are facts about the systems, but others are not. Let's take the example of a toy train. If I'm standing here with a toy train and handing you the toy train, right, and say this accurately reflects a train, it's just bigger, right? Then you have a super good idea, right, how the train is going to look like. But then you turn it around and you see it runs on little rubber wheels. You don't think that the train runs on rubber wheels because you already know. You already have the domain knowledge. You already know where the analogy doesn't hold. But if we talk about abstract systems like Kubernetes, software systems in general, right, and somebody talks in analogies, I do not know where the analogies end, and I may draw the wrong conclusion. That is why analogy models, in my world, analogy models are not suitable models for documentation or technical communication.
Any other questions?
Yeah, just a question as I'm absorbing and trying to map out my own mental models as you lay them out. In the way that you laid out execution, does that mean that there's no such thing as a race condition in Kubernetes?
That very much depends on how you define race condition. That is one of the not necessarily sharply defined terms, right? But yeah, what would you think about when you say race condition? What do you have in mind?
Collision of execution and resource allocation.
Well, so in general, right? If you have a race condition, that is, or let's try to find a definition to apply to Kubernetes. Is where the outcome is different, right? Whether action A happens before action B or action B before action A, right? And so in theory, yes, it's absolutely possible for Kubernetes to run into race conditions. However, careful design actually does avoid that. So race conditions are generally avoided, but and where they happen, they're usually considered bugs.
And then back there.
Yeah, with the carefully designed Kubernetes, how would you go about with health monitoring and like security from OWASP and stuff like that? Is that just automatically on Kubernetes, or is there like?
I'm totally out of my comfort zone. I do not know. I would love to answer that question. And usually, if I don't know something, I ramble on for half an hour, and if I know something, I have one sentence. So, so unfortunately.
So I've only recently started kind of getting into the world of Kubernetes because I'm having to write documentation for an integration with a stateful application to run on Kubernetes. And so the stateful world is like a totally different, it's just kind of coming into the Kubernetes spotlight. And so a lot of users, I feel like, come to this documentation from all different levels of knowledge about Kubernetes. And we're only like, you know, when I'm writing just one topic on one sort of functionality, it will only use like a cross-section of Kubernetes concepts, right? And so when I'm talking about Kubernetes objects and their relation to each other, and you know, it's like, okay, you need to worry about this object state in this certain condition, and I'm just kind of, I don't know kind of when to stop the transfer of information. You know, like when is it okay to stop, you know, and where I feel like that enough information transfer has been complete, or else I could just take one topic and explain Kubernetes if I just keep going, right? Yeah,
you're absolutely right about that. So number one, we are also still grappling with find a path, right? From the very first step, when you introduce what is Kubernetes, when you introduce control plane and data plane, how do we get into controllers? How do we get into Kubernetes objects? What even is a Kubernetes object? We have been trying to find a definition for half a year, right? And couldn't land on one just yet. And so there is the problem of breadth, right? But there is also the problem of depth, right? In how much detail do you actually go into it? And this is one of the situations where model hierarchies come in, and actually strict model refinement. So we have one model of the Kubernetes deployment object, of the Kubernetes deployment controller, right? That talks about Kubernetes deployments and the deployment controller in very, very abstract terms. It just talks, it's a formal model. It talks about it in abstract terms just in the sense of a deployment exists without ever specifying what a deployment is. A deployment has a relationship to a replica set without ever defining what a replica set is. And you can already on this level, right, explain to the user what actions can the deployment controller take and what will be the subsequent state. And then you add refinements where you then say, all right, here we talked about the deployment abstractly, where I just said there exists a deployment, right? And now let's unfold this concept and see how a deployment is actually structured. And that way you can actually add stepwise more detail, right? But it is a very labor-intensive process because for you're not only coming up with one model, you're coming up with N, right, for one concept. It's very labor-intensive.
So one of the principles that we try to follow is to just add more detail, but never contradict what we say before, right? And that way, and it's hard, like, you know, it's not an easy thing to make sure you do that, right? But we want to make sure that, like, people will learn up to the point where they need, right? And there may be more detail after that, but that's up to them. They can go look at it or not, right? And so it's sort of a difficult thing maybe to structure it that way, but that's the goal, that's the ideal, right? So like say scheduler, for example, right? You can start off with a very simple thing is the scheduler, you know, determines like which node to schedule pods, and then later in another iteration you can add the like information about taints and tolerations and stuff. And so at some point, you know, they may need to know about maybe before they don't really need to know about taints and tolerations. They're like, okay, cool, the scheduler handles that. But then if it's like, okay, I'm gonna write, you know, my own scheduler control, I need to understand how this one actually works, or make sure like I don't, you know, bump into the default one, right? So like that is the ideal that we're going for, because there's this other philosophy which is called like lie to children, which we absolutely hate, which is that you give someone sort of just like a basic, you know, model or idea, and like you say, okay, this is how it works, but then later on you're like, no, it's not really like that, it's more like this, right? And a lot of like maybe college you know, courses have been like that, and we do not subscribe to that philosophy. We want, you know, everyone starts off at the beginning the same, we give you the same information, and we just add more detail. So you can go up to the point where you need the information. So like, because there are other roles, you know, adjacent to you know, the Kubernetes, besides engineers and tech writers, right? There are like, you know, solution architects, there are like technical marketing, there are, you know, UX designers, and they need to know how Kubernetes works, but they don't necessarily need to know all the details. But we want to give them the same exact information so that they understand it in the same way, so that we're all on the same page. Any other questions?
If not, we come to off the cuff. Can we kill the recording?